Okay friends, today in this class we are going to discuss about geomorphological modeling. So, now the question arises, what is a geomorphological model? And first question is, do we really need a model, and what are the different type of models, how they are prepared, and what is their utility? In this class we will discuss in detail what are these geomorphological models and why really we need the geomorphological models. So, if you see here, we have different problems nowadays the earth is facing. The foremost problem is our global warming. So, it is such a huge problem that is affecting our water, affecting our vegetation, affecting crops, affecting soil, affecting our day to day life, affecting our day to day activities. So, that is why though we have one problem, but affecting different aspects of life. So, now the question arises, how geomorphological model can solve this problem. Now, see, applied geomorphologist equipped with techniques. So, we have models, we have knowledge, we have different techniques. Now, using the knowledge and techniques, we have to solve this problem. But before solving the problem, we must first understand the problem. So, problem understanding and problem solving, in between this gap is the geomorphological model. So, that means geomorphological model, these are the bridges that interact, or the bridge between this problem understanding and problem solving, in between how this problem is behaving in between. So, that is the geomorphological model. So, we have applied geomorphologists, they are equipped with different techniques like terrain mapping, then remote sensing, then geographic information system, GIS, those can contribute from environmental management and program easily. So, using this knowledge, using certain suitable materials, we prepare geomorphological models. Through these models, we understand the problems and we predict for the solutions. This is the main use of geomorphological model. So, here by definition we can say the process of simplifying real landscapes to manageable portions is called model building. That is very important. Manageable proportion, it is important. Suppose we want to prepare a model for the Himalayas, or for example, here this figure given, it is the model prepared for the San Andreas fault of America. Now, you see, if we are preparing a model, here when we are showing the fault, here the oceans, here the continents, and different sub faults they are arranged, the hill slopes they are arranged, all those things are there. So, that means what is in the real landscape, that all those components should be reflected in our model. So, simply it is this model which is manageable proportion of this area which is representing the San Andreas fault. So, if we are preparing a gigantic model, if large model, we are not able to manage it. So, that is why by definition geomorphic model, it should be a miniature, it should be a replica of the real landscape, but it should be manageable. So, defined in general way, the geomorphic model is a simplified representation of some aspects of real landscape that happen to interest of geomorphologist. Simplified aspects of real landscape, that means here in this particular example, if you see real landscape, we have this San Andreas fault, we have this associated other faults, we have associated oceans and associated continents, the hills and whatever may be the, and the model, all those components has to be reflected, then it is called a model, otherwise simply nothing, it is cannot be called a geomorphological model. So, that means each and every components has to be precisely placed with proportional scale, that is important, with proportional scale. For example, suppose we are preparing a model of the San Andreas fault and we are only highlighting the fault and not the surrounding. So, it is not the model. So, model, that means if we are considering a particular area, particular features included within that area, all those features and this total area has to be proportionated and finally reflected in the model, then it is called a geomorphic model. So, why a model is required, that we have already discussed. Problem understanding and providing a solution to the problem, geomorphic problem I am talking about. So, in between this gap is filled by geomorphic model. So, that means proper understanding, a problem has to be understood properly. So, proper understanding of the problem, the processes involved between the system, to understand those processes we need geomorphological modeling. And once a model is prepared, that become easy for a geomorphologist to predict the behavior of the system in future. So, geomorphological modeling, it is very much essential for predicting a geomorphic system for its future activities. Now, geomorphologists built models at different levels of abstraction. For example, if you see here models, how we can classify it. You see model, there are three, it is classified into three different ways. One is called hardware model, then conceptual model, then mathematical model. Hardware model means here hard material, here material is used. So, that means in the last figure as we are discussing, suppose we want to prepare a model for the Himalayas. We have to show this MBT, MFT, MCT, these rivers, these peaks, the glaciers, all those things, and with a proper scale. So, in that case, if we want to prepare a model using these kaolinite clays, these beams, we are using this clays and other material available, we are preparing a model. So, that is called hardware model. That means, we are using material. This material has to be chosen precisely. That means, in nature, whatever the materials are there, for example, in the Himalayas, we have rocks, we have sedimentary rock, we have metamorphic rock, we have igneous rocks. So, we choose the material, its properties should be identical to those materials, otherwise the model will fail, that will not predict precisely. So, not the same material, but it should be identical property of that material which is present in nature. So, that means these are called hardware models. So, that means we are using some material there. Then second type of model, it is called conceptual model. That means concept, it is only in our mind. So, we saw a problem, this problem we thought process started. So, we could have model in our mind that this could be the different, this could be the problem, this could be the possible causes, and this will be the product. So, to consider this problem, to solve this problem, there are different thoughts, there are different possible regions that is going in our mind. So, in conceptual model, simply it is, that means we think for different concepts. This could be the concept, this could be the regions in, that is in the this, if this problem mix, then this will be the solution, or this will be another problem, so like that. So, that means conceptual model, it is the concept, it is the solution which is different possible solution in between, this is it is remain conceptual, this is conceptual model. Then mathematical model, once we have a conceptual model, to predict it, that conceptual model means it is always in your mind, but to come it in mathematical prove it, to prove it, yes, whatever we think in our mind, it is true. To prove this conceptual concept, we need some mathematical solution to it. So, that is mathematical model, some quantified model. So, that means three types of model, one is hardware model where material is used, conceptual model material is not used, mathematical model, that means the concept to transform or to reflect in a real world with some quantity, with some solution, with some relationship, that relation is expressed in mathematics. So, that is mathematical model. So, in hardware model, the first and foremost and the simplest method is the scale model. Scale model means we are decreasing the scale or increasing the scale. Suppose for example, here for your concept, one scale is 1:50,000, another is 1:10,000. Which one is large scale? It is 1:10,000 is a large scale map. So, scale model here, if as we consider scale model is simply we are decreasing the scale, we are reducing the scale. Understanding the whole Himalayas at a time, it is not possible. That is why we reduce its size to a tabletop. So, once we are reducing a size, that means we are changing the scale, and it is a hardware model, scale model, it is a part of hardware model. So, that means we are using some material to prepare artificial Himalayas on our tabletop and showing all those features, whatever these features we require to show, all those features we show in this model, and finally, it is a scale model. Scale model are miniature and sometimes gigantic copies of the system, but once we say it is gigantic copies, that again I am saying it should be manageable. Until unless it is a manageable scale, manageable size, that is not a model. Example, relief model fashioned out to suitable material such as plaster of Paris. If you see in this figure, we have a glacial system, model of a glacial system, we have plaster of Paris, prepare the glacial system here, the mountains, all these glacial erosional feature, the arcs, the carries, this glacial valleys, and finally, this movement of this glacier, then glacier melts here, these are the glacial lakes, then the rivers. So, that means in a glacial environment, whatever these features are, those are modeled through artificial material with proper scale, and this is called a scale model, scale hardware model. Models made using material identical to those found in nature, this is very much important. Models which is formed by identical materials, not the same material, but with the dimension of different scale down can be used simulate the dynamic behavior, because we want to understand the problems, because we want to predict the future. That means, the model has to be dynamic, because our geomorphic system is dynamic. So, if I prepare a model and it throw it somewhere, so it becomes a toy, it is of no use. So, that means model has to be dynamic, like the geomorphic process, a glacier is moving. So, that means in a model whatever depicts, whatever represents a glacier, that must also move in that particular rate where the glacier is moving. So, that means I want to say it is a scale model is a hardware model which uses the material identical, that is representation of this nature, but not the same material. But if we use this same material, then we will put in problem. What are these problems? We will discuss here. The advantages of this type of scale model, in which the geometry and the dynamics of the model and the system are virtually identical. That means, already we have discussed, if we are modeling a landslide, we are preparing kaolin clay or something clay or whatever this material we are used. So, landslides means we are sliding one part of the land surface. Similarly, in our model, this type of land surface has to be slide down, then it is a model. And similarly, if you are sliding at a different rate than this actual, then it is not a model. So, that means scale has to be maintained, rate has to be maintained, material properties has to be maintained. That means, if by considering those aspects we are using some material and preparing a model, then it is called a scaled model and hardware model. Other scale models use natural material, but that has certain disadvantages. What are the disadvantages? For example, suppose we are modeling a lacustrine environment, a lake is there, we are modeling it, and we have 7 meter of water. For example, we have 7 meter of water depth, and we are creating a model 1 of 1000 reduction. So, that means this water depth of 7 meter will be 0.7 millimeter. So, once 0.7 millimeter depth water is there, if you are using sand representing the lake sediments, this sand due to surface tension will float on this water. So, that means our purpose is not solved. So, that means choosing the material for geomorphic modeling, it is also important. So, that is why we use identical material, but not the natural material as it is. The same thing we have discussed. For instance, a model of an estuarine made of a scale of 1:10,000, an actual depth of water 7 meter is represented in the model by layer of water 0.7 mm depth. In such, the layer water surface tension will cause enormous problem, and it will be impossible to simulate tidal ranges and current also, because in lake we have some tides, we have some currents. With 0.7 mm depth of water, it is not possible to simulate those features. So, it is not a model. Similarly, the sand that we have discussed, the sand will float on the surface of water, it is due to the surface tension. So, that means identification of material and choosing a scale, both are equal important for preparing a geomorphic model of hardware nature. Another type of model is analog model. Analog models are more abstract scale models. The most commonly used analog models are maps and remote sensing images. Similarly, here there are two subdivisions, one called static model, another called dynamic model. Suppose geological map or topocity of any area, this is a static model. Static model means, suppose for example, we are using a topocity mapped on 1965 for example. So, that means whatever the information available in 1965, those are embedded in that is map. And after 1965 to 2019, whatever the changes has been taken place in that area, those changes are not reflected on this map. So, though we have a geological map or a topocity, that is static model, we cannot predict anything on that. But if we have dynamic model means it is change can be predicted, change can be detected. By showing a change detection, we need dynamics in the system. So, that topocity can be used as a dynamic model if a series of topocity is available. For example, for a particular area, for example, in this area, we have a topocity of 1965, we have a topocity of 1970, we have a topocity of 1980, 2000 and 2010. For example, a particular area we consider. In that area, whatever these features available in 1965, if we compare with 1970, then there will be change. In 1980, there will be another change. In 2000, there will be another change. In 2010, there will be another change. So, that means these changes can be detected through a series of map in a particular area, and those models, they are called the dynamic models. Similarly, case of remote sensing image, suppose we have only one image, that means during this image acquisition, whatever the material was there, whatever the information available in the land, that is embedded there, that is a static model. But in Landsat series or in IRS series, after a particular day or a particular time interval, there will be same image will be acquired for the same area. So, if we compare those images and information is extracted from that, preparing a model or detecting that change, that can be called dynamic model. So, that means I want to say here, static model, they cannot be used for prediction purpose. They cannot say anything what will happen in future, but in a dynamic model, it always predicts for the future. that this change, this is the change and this is the rate of change, that is important to say. Change is not enough, the rate of change is enough, that means quantification. If we are quantifying the system properly, that means we can precisely modeling, we can precisely predict for the future. On the map, the surface features of a landscapes are reduced scale and represented by symbols. Remotely sensed image represent a reduced scale certain properties of the landscape system, similarly the topography also. And if you see here, we have satellite image, we have topography, we have aerial photographs. So, they are called the static analog model that we have discussed. That means, only maps or topographies of aerial or satellite image or aerial photographs, if we only consider only one time of those, that is called static system or static model. But if a series of map is available for the same area, and from the series of map we are extracting information and the change, we are detecting the change, then we can predict these are these change and this is the rate of change. So, those models are called the dynamic models. Now, dynamic analog model can also be built by hardwares, which is system size is changed and in which material used are analog, but not the same. For example, if you see here in the first image, we have a river system is modeled. In the systems second, the river, but it is a alluvial fan system is modeled. So, here we have a dynamic, these are the dynamic models, because suppose we are creating some natural material or creating some artificial material of identical characteristics and water, we are putting water here. So, once we are putting it water here, we are creating a river system. So, in the river system somewhere there will be sidebars, there will be some ripples, there will be some dunes, whatever these features available in a fluvial system, these features will form. We increase water, we increase the velocity, we increase the slope. So, that means we can detect the changes, how the fluvial system is changing. Suppose for example, we increase the slope, instead of this river system looking like there is a braided system, meandering system, that will create a braided system. Similarly, we increase the sediment, bars will form. We decrease the sediment, water will erode its valley. So, that means through this we can predict the change also, and these are called the dynamic analog models. Here material is used and the system dynamics, the geomorphic dynamics can be studied. The analog material simulate the dynamics of the real system, that already discussed. If I am preparing, we are using the analog material, the system dynamics can be reflected, can be studied through it. In laboratory, the clay, the kaolin can be used in place of ice to model the behavior of the valley glacier. Similarly, difficulties arise this kind of analog model when problem finding material identical to the natural material is there. It is very difficult to find out the material which are identical to the natural material. This is a challenge to the geomorphologist. But above all, we prepare geomorphic models. Through the geomorphic models, we study the system, study the dynamics of this geomorphic system, and we predict for the future. This is the applied sense of geomorphology, applied aspects of geomorphology. Another model is conceptual model that we have discussed already. Conceptual model, that means by looking a problem, different concepts, different possibilities comes in our mind. That means we create some conceptual models by looking at problem, and that conceptual model has to be verified and should be supported through quantification by the mathematics. That means it is a mathematical model. So, conceptual model until unless it is reflected through mathematics and related to the real world, it remains a conceptual model. It is of no use. Until unless our concept has to be mathematically proved and has to be real world, it is related. It can predict the future. Yes, whatever we are predicting, whatever the concept in our mind, the same thing is happening in the nature. And same reason, until unless it is proved, the conceptual model becomes a conceptual model. It is of no use. So, conceptual models are initial attempt to clarify loose thoughts about the structure and function of a geomorphic system. So, once the thoughts comes in our mind, to prove this thought to be right or wrong, we have to refine it, we have to relate it to this to the geomorphic system or geomorphic process going on. If our thoughts are proved to be right and the rate again the mathematical relationship is built up, then the conceptual model is converted to a mathematical model. For example, if you see here Nepal earthquake in 2015, it creates some fractures in the Ganga plain, surfacial faults, very wide fractures were developed. In the geological past also, we had some wide fractures faults in the Ganga plain, and through those faults we created some terminal fans, some small fans. If based on this fan by their age of formation, this conceptual model could have been developed if this is a suppose for example, if we take a graph here, this side we take the edge and this side we take this fan. So, it could have been plotted a graph with edge how the fans are formed, and finally, we are coming to its mathematical solution, we are coming to a mathematical formula of the straight line, and we could have been predicted this 2015 earthquake. So, that means I want to say until unless this concept is mathematically proved and it is related to this ongoing geomorphic process which is going on in front of us, this conceptual model has no meaning. It becomes in concept forever. So, that is why to convert the conceptual model to mathematical model, we should do some experiments, mathematical experiment, mathematical modeling. Like that we are discussing here. Now, you see these are the surface faults, they are the surface fractures through which sediment is eroded here and deposited here, creating terminal fans. If I can date it, these sediments, the bottom sediments, these bottom sediment, we can say when this faulting was occurred. So, we have faulting occurred here in this time, then next fault occurred in this time, next fault occurred in this time, next fault occurred. So, that means we are putting in a straight line, we are fitting a straight line, and the straight line y equal to mx plus c. So, it is a mathematical formula, through this mathematical formula we can put it. So, through which we can predict when the next event of earthquake or next event of surface rupture is reserved. So, that means by this way we can predict for the future. So, conceptual model through mathematical relationship, it is converted to a mathematical model. Through those mathematical model we predict what will be the future scenario. So, this is all about this geomorphological modeling. So, we have discussed this mathematical modeling. A mathematical model is testable by matching predictions against observation. This is very important. Only creating a mathematical formula and relating this concept to a model is not enough. Mathematical model, then it will be proved to be accurate or it is workable if it can relate the present day observation. What is going on in a geomorphic system in front of you? If that can be predicted through the mathematical formula and it is proved, yes, whatever the mathematically we have predicted, we have proved the same process is going on here, then this mathematical model will be a truth model. Otherwise, only becomes a mathematical formula only, which has no meaning. So, mathematical model is testable by matching the predictions against the observation. we have observed something, our observation is mathematically modeled, mathematically related, it is formulated. Through this formula we are coming to a result, and this result is predicting that this will happen after this year or some so. And if it happens so, then our mathematical model is right, otherwise there is nothing like a model. So, the same thing can be shown here in this figure. We have these terminal fans, different terminal fans associated with different faults. So, now these are these episode, these are the tectonic episodes, first episode, second episode, third episode. In between we have a tectonically stable period here, we have a tectonically stable period here, and in between we have small tectonically stable periods here. So, here if we arrange those in graphical format, we can say in episode 1, here in episode 1 we have time percentage more, fault percentage less. So, that means in more time there was less faults. So, that means the rate of tectonic activity was less, but here less time more faults. That means here the rate of tectonic activity, the rate of surface rupturing process, it increased. Similarly, in third episode here this time percentage is here, fault percentage is here. That means more faulting episode, more surface rupturing episode is associated. So, that means if we predict from 10,000 years, 9,300 years up to present day, up to 0, then we can say in Ganga plain the rate of surface rupture process has increased from early Holocene to present days. So, this is the prediction, this is the prediction. Through this prediction we can say when the next surface rupturing event is waiting. Now, data source for geomorphological studies. We have modeled the geomorphology. Now, we need where from which place, what is the different source we can extract data to prepare these models. Data should be available there. The first and the foremost is satellite image of different series, of time series, so that at different times the information can be extracted. Then aerial photograph, then toposheets, isn't it. So, these are these different source from which data can be extracted. Apart from that, there are some organizations like CWC, like Irrigation Department, like Geological Survey of India. So, from there the data can be also extracted. So, in which whatever the aspects, on what aspect you are working, based on that aspect you have to explore where from I can get those data. If you are getting those data, using the data, the past data, using those past data you come to a mathematical relationship, and through this mathematical relations, through this mathematical formula you predict for the future, then a complete set of geomorphological model you can prepare. Then from this data source elaborating more, these are these different data, different symbols, map symbols. If you have, suppose you are given a toposheet, but you do not know which symbol is representing what, it is of useless. So, that is why understanding or recognizing the field symbols, recognizing the map symbols, that is also important. So, if you see here this is closed contour, for example, this is closed contour, this is dotted contour, not sure. So, these are the canals, the roads, the rivers, the rocky portions, the meanders, is not it, the swamps. So, there are different symbols that has to be understood, and the symbols has to be properly understood when you interpret a geological map or a topographic map. The only way fully to appreciate landforms is by field observation. Without field there is no geology, no geomorphology. As a geomorphologist or a geologist doing remote sensing, preparing model, extracting data from map, extracting data from reports, from research papers, it is not enough. You must have to visit the field to see the real life what is going on there, how the geomorphic process is acting there. So, until unless you visit the field, until unless you see in the field how the geomorphic system is working, you cannot prepare a geomorphic model. So, apart from that, we have already discussed bibliographic source material, research paper, different institutions are there to provide you the data. Based on those data, you come to mathematical model, you come your observation and you prepare a model and predict for the future. So, landforms, if you say landforms that vary size from small to very gigantic size, and during preparation of a model you should be cautious that what are the material, what are the scales you are choosing that must be suitable for this for predicting the future, that must be suitable for these models you are representing, is not it. So, that is why if I conclude this today's class, geomorphological modeling is very much useful for predicting the future. If you are able to understand the problem, you can predict the future in between the geomorphological model that work to understand the behavior of this problem, is not it. And before preparing the geomorphological map, you must be sure this geomorphological model, you must be sure the material and the scale you choose that must be identical to the nature, otherwise your model will not work. And second thing is that you must visit to field before preparing a geomorphic model. You have to see how the system is working, until unless your model will not progress. That means, you cannot understand this system properly, you cannot understand the problem properly. So, this is for the today's class. Thank you very much. We will meet in the next class.